it should be well established at this point that forces are vectors, and they have both magnitude and direction. What I want to talk about now is a special vector, the unit vector. What is special about the unit vector is it has a magnitude of 1. And since it has a magnitude of 1, a unit vector gives direction. Or that is its main purpose. So let's say we start out and we have a vector A. A is equal to 8 times the cosine of 54.7 I plus cosine of 54.7 J plus cosine of 54.7 K. So the bracketed quantity gives us direction, and the 8 gives us a magnitude. If we multiply this whole thing by 1/8, the 8 and 1/8 will cancel and go to 1, giving it a magnitude of 1, making this a unit vector. If we go through, A will then be equal to 0.5779 I plus 0.5779 J plus 0.5779 K. And that is our unit vector for A. If this is a unit vector, its magnitude should equal 1. We can simply do this by saying, by using Pythagorean theorem and saying the square root of 0.5779 squared plus 0.5779 squared plus 0.5779 squared is equal to 1. And if in fact you go through, you find out that if you do this, it equals 1. It's a unit vector. So based on this, we can go back and make a simplification. We had a vector, and we just said that theta x, theta y, and theta z were equal to 54.77. Based on this, all we did to get to this 1 is substitute, simplify to get 0.5779 I, j, and k, and then square and take the square root of this. So let's first things first say we want to get rid of the square root, and we can get that by squaring both sides. But if you square 1, you're always left with 1. This 0.5779 squared is nothing different than saying the cosine of theta x, theta y, and theta z squared. So for a unit vector, the cosine of theta x squared plus the cosine of theta y squared plus the cosine of theta z squared is equal to 1. Now, let's say we have a unit vector where theta x equals 30 degrees, theta y equals 60 degrees, and theta z equals 12 degrees. What I would want to know is this a unit vector? Well, we can find out if the cosine of 30 squared plus the cosine of 60 squared plus the cosine of 12 squared equals 1, we have a unit vector. It turns out if you square all these and add them together, you get 1.99, which definitely does not equal 1. Why? Well, it's simply because when you're looking at a unit vector, you can't just pick, or any vector, you just can't pick any angles you want. Only two angles ever are independent from one another from the third. So what we've created here, if I draw x, y, and z axes, if I say that theta x is 30 degrees, so we're over here in the positive x quadrant, and cosine y is 60 degrees, we're somewhere up here in the positive x quadrant, and theta z is 12 degrees. So theta x and theta y give us a vector that kind of looks like this. There's no way that the angle between the z-axis and that vector can be 12 degrees. There's no way it can happen. All the angles are interconnected, and there is actually a subset of unit vectors. Not any random three angles can be a vector or a unit vector. Now, sometimes it's useful to be able to find how a force is acting in a direction or how it is related to a line. So let's say we have a line and we're going to call it line A. And we have some vector acting at some angle theta with the line. We want to know the components that are perpendicular and parallel to the line. Another way of saying this, we want to know that what component acts along line A and what component acts perpendicular to line A. Now, in 2 dimensions, this is really hard. And I say that ironically. If I want to know how much of this vector acts along line A in 2D, well, A parallel is just going to equal A cosine theta. A perpendicular is just going to equal A sine theta. And I say, wow, to that. Now, what isn't so rudimentary is how does this work in 3 dimensions? In 3D, it's not so simple as A cosine theta, A sine theta. In 3D, the easiest way to determine this is using the dot product. And the dot product is given as A dot B is equal to the magnitude of A times the magnitude of B cosine theta. So this is the dot product between 2 vectors. And A dot B is given as AX times BX plus AY times BY plus AZ times BZ. And this gives us a scalar or a magnitude. And this makes sense because when we're looking for a force acting along the line is already giving us direction. So when we do dot products, it gives us a magnitude or a force. Now, this line A that we're looking at is not a vector. It is a direction. So if you want to know how a force acts along a line, you're not doing A dot B, you're doing A dot U, where U is the unit vector, right? So this whole thing simplifies to A dot U equals the magnitude of A cosine theta, because the magnitude of B is 1 because we have a unit vector. Now, once we know that the force is parallel, and I'll call it A sub A to line A, is equal to A dot U, or the dot product between A and the unit vector representing the line, we can use Pythagorean theorem to find the perpendicular component, A sub A perpendicular, by just saying that is equal to the square root of A squared minus A sub A squared. And all this is doing is saying A squared plus B squared equals C squared. This A is the magnitude of the vector minus A sub A squared. So that is the magnitude we found parallel to the line. If we subtract that from the vector and take the square root, that will give us everything that's left, which is the perpendicular component. Now, just one thing I want to talk about right here is the fact that there is another operation called the cross product. This is not really being covered in this course because this course is taken concurrently with linear algebra, and to really be useful and find the cross product in 3 dimensions, you need to be able to find the determinant of a 3x3 matrix, which is not so simple. But just to give you an idea what a cross product will give you, if you have 2 vectors, we'll say A and B, the cross product will give you a vector that's perpendicular to the plane of those vectors, that's perpendicular to the plane of those members, and has a magnitude. So this blue line is A cross B. What it gives you as a magnitude is the area on the plane encompassed by these 2 members. And basically, this yellow region gives you the length of this vector. Now, we won't be using cross product at all in this class. I just wanted to be complete and make sure that you had heard of the cross product and what it gives you. The important things to take from this video are that the unit vector gives us pure direction, and if we want to find how a force relates to a line in space in 3 dimensions, we can use the dot product and of a vector and a unit vector representing the line to find how much force acts along that line.